Hi everybody. For this video, we're going to talk about polar equations and graphs. So recall previously we're using these equations, this relationship over here, to relate rectangular coordinate to polar coordinate. This time we're going to go ahead and use these same equation, same relationship, to convert rectangular equations to polar equations. And of course, when I say rectangular equation, I mean the equation that uses the rectangular coordinate system, and similarly, polar equation is equation that uses the polar coordinate system, right? This is just a shorthand way of saying it without sounding redundant. We're going to go ahead and convert from rectangular equation to polar equation first. This is the easier route. Take a look at our first example, y equals to 3x squared. We're just simply going to use the relationship of x and y to substitute out these y and x in this equation. So y here is equal to r sine theta, and then x here is equal to r cosine theta. So you have 3r cosine theta squared. Then we have r sine theta equals to 3. Here we get to distribute the exponent, r squared cosine squared theta. Now I see an r on both sides. I can go ahead and divide r on both sides. I can do that because I know r is always positive, or rather non-zero. Because the only zero r is when we're working with the pole, the origin. So dividing by r, we have sine theta equals to 3r cosine squared theta. Typically for this kind of equation, you want to solve for the r. So what I want to do here is to divide both sides by 3 cosine squared theta. Okay, and the end result for that is simply, I'll write the r first, equals to sine theta over 3 cosine squared theta. Now this as is already good enough as a polar equation, but typically we want to simplify this as much as possible, or rather make it more pleasant to look at, I suppose. So what I'm going to do is simply break this apart a little bit. So this divided by 3 on the bottom is just simply 1 over 3. And what I want to do here is to stack sine theta on top of one of the cosine theta, and then leave the other cosine theta on the side, so 1 over cosine theta. Now you can probably see the reason why I want to do this, because r equals to 1 over 3. Sine theta over cosine theta is also known as tangent theta, and 1 over cosine theta is known as secant theta. And this right here is a much better answer. And that's usually the answer we want to take. Going on to example number 2, you should pause the video for a quick second to see if you can follow the step from the first example to see if we can do this one. Here, I'll even move the work up so you can see. Okay, let's take a look at this, see if you got this right, or if not, then at least take notes. Same here as before. We're going to substitute x with r cosine theta squared, 5 substituting y with r sine theta to the third. Distributing powers, I get r squared, I get r squared cosine squared theta equals to 5r cubed sine cubed theta. Here, I play the same game as before. You typically want to divide out by the lower power of r. So here you get r squared on both sides. Now we got cosine squared theta equals to 5r sine cubed theta. Again, I want the r to be by itself, so I'm just going to go ahead and divide 5 sine cubed theta on both sides. Okay, and once again, I'm going to go ahead and write the r first. So r equals to cosine squared theta over 5 sine cube of theta. And I kind of want to play the same game as before, right? So break this apart so I can write this in a slightly more pleasant way. So the over 5 becomes a 1 over 5. I will stack cosine on top of sine. So cosine squared theta over sine squared theta, right? I need to match the power and then leave the rest of the power of sine on its own. So 1 over sine theta. This way I can finally convert everything into a more compact trig equation. So 1 over 5 cosine over sine is also known as cotangent theta. So in this case, cotangent squared theta, because cosine and sine are both squared here. And 1 over sine is cosecant theta. So that is your final answer. Not too bad once you remember to substitute the right equation for sine and cosine. Sorry, for r and x using sine and cosine. Moving on to the last example of this type of problem. Here we see x squared minus y squared is equal to 4. And this one is going to work out a little bit more kind of special, a little bit more different than the other ones. So let's take a look. We start off the same though. We start substituting this x and y with the corresponding formula in terms of polar. So we have r cosine theta squared minus r sine theta squared equals to 4. Distributing the powers, we get r squared cosine squared theta minus r squared sine squared theta equals to 4. And now I see r squared on both of these terms. I will go ahead and factor that out. So I get r squared times the first term. If I factor out r squared, I get cosine squared theta. Same thing with similarly with the second term, factor out r squared, I get minus sine squared theta. And again, that equals to 4. Now, not much is happening here other than the fact that I can take this and substitute out with our trig identities, right? This is one of the, I guess, 4 technically equations, 4 similar representations for the double angle formula for cosine. In fact, this is the most standard double angle formula for cosine. So this thing right here just becomes cosine 2 theta. And again, the right hand side is equal to 4. Now to get r by itself, I divide it by cosine 2 theta on both sides. So here I actually get r squared equals to 4 over cosine of 2 theta. And if we kind of play a similar game as before, we write that as 4 times 1 over cosine of 2 theta. And that's just another way of writing 4 secant of 2 theta. So what we have so far is r squared equals to 4 secant 2 theta. Now this is where it's going to work out a little bit different than before. Previously, we almost want the r to be exclusively by itself. In other words, we want what we call a explicit formula of function of theta, right, for r. But this time, if you want r to be by itself, you got to take square root of both sides. If you take square root of both sides, you get r equals to square root of 4 secant 2 theta. And then we can take out the 4, right, by taking it out as a 2 out of the radical. But let's not worry about that for a quick second. The idea here is when you take the square root on both sides, you actually have to do plus or minus. What this does is it breaks the function into 2 pieces. R equals to positive radical 4 secant 2 theta, and r equals to negative radical 4 secant 2 theta. So if you are using it that way, you have to deal with 2 different functions. So in this case, it's actually more beneficial to leave the answer exactly as this. This way, you have a implicit function, but it's a very easy implicit function. Implicit in this case means implied. We know a relationship between r and theta. It's just not obvious exactly what's happening with r and theta. Usually it happens when both sides are part of a function. In this case, the left-hand side here is also a function of r, right? It's not the r by itself in the traditional sense. Okay, but because of this nature of having to deal with two separate functions of pluses and minus, this version is a little bit better. The boxed version is a little bit better. So this is a type of problem that is a little bit unique compared to before. You are going to see a couple versions of this kind of idea in calculus in the later chapter 2 of calculus. So it's a good idea to get used to this right now. Okay. Moving on then. This time, we're going to go ahead and convert from polar equations to rectangular equations. We have to be able to do both. Now, we're going to leverage the same relationships, but notice here, we have r equals to 2 cosine theta. Now, I'll just go ahead and write down these relationships again, just to remind you here. But r squared equals to x squared plus y squared. That's coming from the formula for the r, right, in terms of polar. But the formula we typically also use is taking the square root of both sides. We get r equals to square root of x squared plus y squared. Similarly, for x, we typically use r cosine theta, and for y, we use r sine theta, right? Just the relationship we had before. So if you look at this equation as is, right, this equation as is, the r equals to 2 cosine theta equation, there's no easy way to directly substitute things in. You have to either solve for r using this equation, rather solve for theta using this equation by dividing r both sides, and you have to use this equation, which is dealing with a big radical. So there's an easy way of doing that is instead of working with this function directly, what I'm going to do is to take this function. I'm going to multiply the entire equation by r. Basically multiply both sides by r. Now, of course, if I multiply both sides by a non-zero number, I'm not changing the question. But what that will give me is after I distribute, I will get r squared equals to 2r cosine theta. And now we can see a very easy substitution. R squared is equal to x squared plus y squared. And r cosine theta is equal to simply x. So the equation just becomes x squared plus y squared equals 2x. Now technically this is again already a function of rectangular coordinates, but we can do a little bit better to see exactly what this function does. Well, the way we're going to do that is simply by subtracting 2x on both sides, and we get x squared minus 2x plus y squared equals to 0. And now what we can do is we can complete the square using these two terms. Now, just to remind you what completing the square is, I'll go ahead and write this one out. X squared minus 2x, leave some room. We're going to plus some number and minus the same number, so I don't change the question. And then we'll go ahead and copy the rest. Copy and paste. Now, what is this magical number? This number is actually whatever is here in the middle. We're going to go ahead and divide that by 2, and we're going to square that. So it's this number, negative 2, divided by 2, square that. And of course, negative 2 divided by 2 is negative 1. Square that is just positive 1. So we're going to plus 1 and we're going to minus 1. Now, after doing that, the first 3 term becomes a perfect square. It's actually always going to be x plus whatever's inside here. So in this case, x minus 1. This inside is negative 1 squared plus y squared equals to not 0 anymore because I have an extra minus 1 here. So I'll just simply plus that over to the other side. So the right hand side have a 1. So this is the equation I get. And what this does is that it tells us exactly what shape this is. And if you still have a little bit of trouble recalling what this is, remember that the equation of a circle is x minus h squared plus y minus k squared equals to r squared, where of course this is a circle centered at h comma k with radius r. So this equation is just a circle. This equation right here is just a circle centered at centered at 1 comma 0. Why do I no centered at 1 comma 0 with radius 1. Okay. So doing a little bit of extra algebra is going to help us to see exactly what this picture is going to be. Okay, we'll see more about the graphing of polar equations in a little bit, but this is the main idea that we're working with. All right, moving on to the next example. The next example looks very similar, but this one actually has a little bit nice trick to this that will make this problem significantly easier. You can pause the video for a quick second to try it yourself. Like before, I should probably have some of these works ready. Nowhere near this complicated, I promise you. Okay, so let's take a look at this. The reason why this is super easy is because you actually don't need to multiply both sides by r. What you can do is you just have r equals to 3. Instead of writing cosecant, you can write that as 1 over sine. 1 over sine theta. And that's the reason why it's easy, is because then you can just multiply both sides by sine theta and get the following. R sine theta equals to 3. And last I checked, r sine theta is simply y. So your answer here is just simply the equation y equals to 3, which is a horizontal line. Okay. Moving to the last example. This one is also requiring a little bit of algebra, and this one does rely on the first trick that we did learn. So you can try this one if you want. Go ahead and pause the video. Okay. Let's take a look at how this works. We're just going to go ahead and multiply both sides by r. So we got r equals to 2 minus 2 sine theta. Multiply both sides by r. R not squared. What is going on here? After I distribute the r, I will get r squared equals to 2r minus 2r sine theta, and r squared is equal to x squared plus y squared, just like before. The 2r, there's not much you can do about that other than just leave it as 2 radical x squared plus y squared. Again, there's not much you can do about this one. Here, r sine theta, this equals to y, so this is minus 2y here. Now, I do want to get rid of that radical, so I need to somehow square both sides, but I cannot square both sides just like this because this subtraction here is going to get in the way of canceling the radical. So what I want to do here is to add the 2y to both sides. So I get x squared plus y squared. Oops, that should be a 2y. Typo. Plus 2y equals to 2 radical x squared plus y squared. Now this might look a little bit complicated, especially if you imagine what's going to happen next, right? But the good news is for this type of problem, you don't have to rely too heavily on algebraic simplifications. What I mean by that, of course, is the next step being squaring the both sides. What you typically have to do here is to FOIL out this 3-term polynomial, right? This got 3-term polynomial here. When you square, you're gonna get 9-term polynomial, and then you can combine like terms and all that good stuff. The good news here is you don't have to do that. You can just go ahead and leave it as x squared plus y squared plus 2y squared. Okay, and then on this side, you do want to work out the square, but that's just distributing the square, right? 2 squared is 4, and now here radical and the square cancels out. You get x squared plus y squared. Okay, and again, this is actually good enough for me, good enough for the type of function you're dealing with, because you won't be able to solve this anyways, right? You will not be able to solve this. There's way too many different powers of y, way too many different powers of x, and the interactions between x and y. So there's not really that much you can do. You can try to do more things like FOIL this part out, right? And then of course distribute the 4, and then move things around. But ultimately, you will not be able to solve for either variables. So this right here is good enough to keep as an answer. Go ahead and erase that. Okay, this right here is typically good enough to keep as an answer. So as you can see, something that can be described, so easily with polar, right, with polar equation, end up becoming so difficult to describe with a rectangular equation. And that's really going to be the reason why we want to deal with polar equations, because, well, because of the various capabilities we can graph, that the rectangular coordinate is simply unable to do so. Okay. In the next video, we're going to see how to graph polar equations, so stay tuned for that.